Hi everyone. In this video, we begin with Chapter 9, Differential Calculus 1. And the first thing we're going to take a look at is the learning objectives. So what are they? First of all, we're going to look at the concept of limit. That's something that we're going to study today. Also, the derivative as a gradient or slope function as the rate of change. You might not be familiar with this terminology, but as you advance in the topic, you'll see that all this is quite simple. Finding the derivative of polynomial functions, the derivatives of sine and cosine. In further videos, we'll be looking at the relationship between the graphs of a function, first derivative and second derivative, identifying where functions are increasing or decreasing, different tests for maximum, minimum, and inflection points, kinematic problems, that means physics, problems of motion, involving displacement, velocity, and acceleration. And finally, how to find the equation of a tangent or a normal at a given point. So like I said, maybe you're not familiar with some of this terminology, but as we advance in the topic, you will see that all of this is quite simple. Okay, so in the next slide, you're going to look at a couple of graphs that compare two situations. So on the left, you have a curve and a line going through 2 points, in this case 4, 2 and 10, 4.25. So since this is a distance over time graph, the slope of this line that we see here going through those 2 points would represent an average velocity in that time interval. So from t equals 4 to t equals 10 seconds, you have an average velocity of 0.375 meters per second. So what calculus deals with is with what we see here on the right. It's the same graph, the same line, but in this case, we have a point which is 7.3875 and a line that is tangent to that point. So the slope of this line at that point of tangency would give us something called the instantaneous velocity. So if we calculate the slope of this line, we would get 0.25 meters per second. What does that mean? That means that at that very instant, when time was equal to 7 seconds in this case, the instantaneous velocity would be 0.25 meters per second, represented by the slope of this tangent line. So that is what calculus deals with. Okay, so now we jump straight into 9.1, which is limits of functions. That's the topic. Example 9.1, evaluate the limit as n approaches infinity of 1/2 to the power of n by using your GDC, your graphing display calculator, to analyze the behavior of the function f of x equals 1/2 to the power of x for large positive x values. So what a limit implies is what happens as the variable in the function approaches another value, right? So what if, in this case, n, they say what is the limit of 1/2 to the power of n as n approaches infinity? So that means in the case of f of x equals 1/2 to the power of x, what happens when x has very high value? So what happens when you have 1/2 to the power, say, of 10? Well, this is the same as 1 divided by 2 to the 10, right? If you have 1/2 to the power of 100, that equals 1 divided by 2 to the power of 100. So obviously, the limit as n approaches infinity for 1/2 to the power of n is 0, because these values are getting closer and closer to 0. If you divide 1 by larger and larger numbers, you get closer and closer to 0. So we're going to see that in the next slide where there is a graph. So let's move on to the next slide. And we can see here precisely the graph of 1/2 to the power of x. So you can put this into your graphing calculator, and you will get a function that is definitely getting smaller and smaller and smaller as x increases. So as x, right, because here we're talking about terms of x, but it's the same thing, right? X or n, it's just a variable. So as x approaches infinity, f of x, or the graph, as you can see here, gets closer and closer to 0. So for example, in this table, we see what happens when, say, x is to the power of 13. So if you have 1/2 to the power of 13, you get 1.22070313, and this means times 10 to the power of -4. So that means, what that means is that you get 0.00, one more 0, 1, 2, 2, etc. Right? So this is obviously closer and closer to absolute 0. All right, so next we are on example 9.2, and here they ask us to find the value of the following two limits by using your graphing display calculator to analyze the graph of the relevant function. All right, so the function is sine of x over x. Here they're asking for the limit as x approaches 0. So notice that in this case, it's not the limit as x approaches infinity. But what happens if we plug in 0 into sine of x over x? We would get sine of 0 over 0. And obviously this is undefined, right? This is undefined. Therefore, we cannot really find out what the value of the function is as x approaches 0. In this case, we get the same thing because the limit as x approaches 0 of cosine of x minus 1 over x is the same as plugging in cosine of 0, plugging in 0 minus 1 over 0. And this is also going to be undefined because we cannot divide by 0. So there's no way we can know what these limits equal simply by plugging in the number 0. So what we do is look at the graphs. So that's what we're going to do next. So in the next slide, you will find the graph for sine of x over x. So this is what you would see in your graphing display calculator. That when x is 0, you see a big hole in the graph. That just means it's undefined there. But we can analyze this in a different way. What happens when you approach 0, the value 0 for x, from the left and from the right? What happens to y? Well, let's look at y. As you can see, as you approach 0 for x, y gets closer and closer to 1. So that means that the limit, we would say this, that the limit as x approaches 0 of sine of x over x is 1. Okay, so let's take a look at the next slide and see what happens in the case of cosine of x minus 1 over x. So let's take a look at that. And we can see this situation here. So there's a graph right there of cosine of x minus 1 divided by x. So notice that we have this here. It goes through or close to 0, 0. Notice that at exactly 0, it's undefined. That's why you see an error here in the table. But what happens as you approach 0 as an x value from the left or from the right? So here they're approaching it from the left, and these are the results we get. This is where they approach it from the right, and these are the results you get. Now notice that all of these are close to 0. 0.115, 0.1, 0.005. So the closer you get to actual 0 for x, you get closer and closer to 0 for y. That's why you can conclude that therefore the limit as x approaches 0 of cosine of x minus 1 over x is 0. All right, so the next example is 9.3, and it says find the limit as x approaches 0 of 1 over x squared if it exists. So what happens if we plug in 0 here? We're going to get 1 over 0 squared, which is 1 over 0. And again, this is undefined. But like we said before, there's another way of doing it, which is testing values approaching 0. So let's say that we have 0. What happens if we approach it from the left or we approach it from the right? What happens to the graph? So we're not going to plug in values. We're just going to take a look at the graph, and that's in the next slide. So let's do that. Let's just go to the next slide. And we can see the graph here to the right. Notice that as x approaches 0 from the left or from the right, the function just goes up into infinity, right? Whether it's from the left or from the right, you can see the function increasing to infinity. So that means that 0 is a vertical asymptote. In other words, we can conclude that the limit as x approaches 0 of 1 over x squared does not exist. Why is that? Well, because of the definition of limit. In order for a limit to exist, it has to converge to a value L, right? So we can see that here. Unless it converges to a value, the limit of the function does not exist. So before we end this short video about limits, we're going to recall from section 2.2 the end behavior of rational functions. Since the limit as x approaches infinity of the rational function 3x squared plus 5x minus 1 over 2x squared plus 1 is equal to 3/2, then the rational function y equals 3x squared plus 5x minus 1 over 2x squared plus 1 will have a horizontal asymptote of y equals 3/2.